So to prove this transform, I will show where this transform comes from. It's actually easiest just to start from the result and justify it that way. So we start from the transform, and then we're going to differentiate it with respect to this z here. So this is going to give us dw by dz equals, okay, well w naught is a constant, then we're going to have alpha, and then it's times, well, if you differentiate an integral, you just get the integral, but the integral is going to be with the value z. Okay, so if you think about it, if you, for example, differentiate t naught t x squared dx or something by dt, if you think about what actually happens, you integrate the x squared to get the third x cubed, and then you substitute in the t and the t0. So effectively what happens is the t0 disappears when you integrate with respect to t. You've done the integral of x squared, you get this, but then you substitute in the t into the x squared, but then you differentiate again with respect to t. So in fact what you end up with is just, in this case, t squared. So we're going to end up with this thing, but with little z instead. So we end up with z minus x1 to the minus p1, z minus x2 to the minus p2, dot, 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 little z minus xn1 minus pn minus 1. Then what we do is multiply both sides by dz. So I'm going to take this dz and put it here. So it's a little change in z. We're looking at how a little change in z affects a little change in w. Okay. Then what we do is we take the argument of both sides. So just to remind you that the argument of the product of two complex numbers, easiest to see if you write it as r1, r2, e to I theta 1 plus I theta 2. The argument is theta 1 plus theta 2, so it's the sum of the arguments of the two complex numbers. And similarly, if you've got a product of complex numbers, the argument is the sum of the arguments. So we're going to this is going to give us arg of dw is equal to arg of alpha. And also, you may recall that if you've got arg to some power, then that power comes down. So arg of a complex number to some power, then we just take that downstairs and we end up with p1 times arg of z minus etc. minus p and then finally the arg of this. So this looks somewhat complicated, but actually this is actually remarkably simple if z is on the real axis. If z is on the real axis, arg of z minus xi can be one of two things. If z is to the right of x1, for example, then z minus x1 is positive and arg of this is 0. But if z is to the left of x1 on the real axis, then this is a negative number and we've got the argument is pi. So all of these are either pi or 0. So what happens if, so imagine what happens if we start at z equals minus infinity on the real axis, and we just move along the real axis. So when we start at z equals minus infinity, all of these are pi. All of these arguments are pi because these are all basically negative. Then as soon as we so basically the arg of dw. So dw is really telling us what's happening in the w plane when we change dz. So as dz is changing, we're being told what happens to dw. So the argument of dw doesn't change as we move along the line until z crosses x1. So effectively what we're doing in the w plane is we're moving from the point at infinity, which corresponds in this case to wn, or w5 in this case. So we're actually moving along this line until we get to this point x1. At that point x1, when we cross at x1, this changes from pi to 0. So now we've got pi instead, and pi times p1 is phi1. So what's actually happened is that the argument of w, it used to be minus p1 times pi, it's now 0 instead. So the argument of dw has actually increased by exactly phi1 when we cross from here to here. So that's what we see here. We were moving along here, and then suddenly when we cross x1, the argument of dw increases by phi1. So now we're going to move in this direction, and then the same thing happens when we cross x2. The argument is going to increase by phi2, and so on, right the way around the polygon. And that's basically why it works. The only thing left to say is because it's a conformal map, the points we want are on the left of the line as we go increasing x, and sure enough, the area we want is to the left of the line as we go from w1 to w2 and so on.